So, over the last 50 years, microfabrication technology has greatly advanced many areas of science and engineering. Microfabrication is a way to create tiny structures that are measured in micrometers, which is super small, about 1,000th of a millimeter. So, to give you an idea, a micrometer is about the same width of a human hair strand, while 1,000th of a micrometer is about half the width of a tiny hair strand of a lung cell, for example, which is super small. So creating these structures on such a small scale actually serves many benefits. So smaller structures use less material, which lowers the cost of experiments and resources needed for testing. Many steps in microfabrication can be automated, which speeds up the production and increases efficiency. You can also fit many devices on a small space, so it allows for kind of more efficient experiments, and you can do more testing on it at once. Historically, microfabrication began in electronics, specifically for making integrated circuits. So it was used to make tiny components of a computer. However, most recently, there's been similar techniques being used to make microelectromechanical systems, so small sensors and devices. For example, most common ones are like pressure transducers. Um, so it can be used in a car to monitor your tire pressure, or printers where they use tiny actuators that spray ink droplets onto the paper. So these small devices actually play like a crucial part in some of the advanced technology that are being used every day. Photolithography is a technique that uses light to create a tiny pattern. So it plays a big role in making microchips for electronic devices. The word comes from photo, meaning light, and lithography, meaning a printing method that transferred designs onto a surface like paper. How it works is that it starts with a material called a substrate, which is usually like a silicone wafer where you'd want to create your design. Um, in this case, in this example, it would be the gingerbread man. So a special liquid called photoresist is spread all over the substrate, and this liquid reacts to the light. So in this example, the liquid is applied to the second structure that you see on the photo, and then a mask is placed on top. So it's placed over the photoresist. So usually the pattern is made of chrome, and then it's on a glass surface. Usually it's then exposed to ultraviolet light, which shines through the mask, hitting the photoresist. It causes a chemical reaction, developing two patterns. So there's a positive tone and a negative tone. Usually the positive tone is the parts that are exposed to the light that dissolve away, leaving the unexposed areas of the pattern. So for this one, it would be that it basically like ate away at the gingerbread man, leaving kind of like a hole in the middle. Um, Rather than the negative tone would be basically the opposite. It would leave the little design of the gingerbread man. So photolithography is essential for making microchips that contain billion of electrical parts like transducers and capacitors all packed into one chip. It also provides high resolution, which allows for very detailed and precise designs, which is crucial for electronics. However, the technique has been adapted in tissue engineering to create cell patterns and biomaterials. This has led to new development in material methods for 3D printing biological structures. So we're going to go into more detail on some of the structures that photolithography plays a role in. Photolithography can be used in many different ways to help cell interact with tiny structures made from it. So these are the three main scenarios on how cells relate to structures. First, we have the cell on microstructures. So in this setup, the cell is placed directly on top of the tiny structure. These structures can act like a scaffold, providing shape and features that guide how the cell behaves and grows. However, the material used in these structures must be safe for the cell to encourage them to stick onto them. Because of the material used in photolithography can be toxic, such as the photoresist, like the liquid, they aren't usually used directly for cell growth. Instead, they're used to make molds or masks that create a safer kind of like materials for cells to interact. Second, we have cells in microstructures. So in this case, the cell is embedded within the tiny structure. This approach can allow for more complex interactions and functions, which require careful designs to ensure that the cells can survive and thrive within the new environment. Third, we have cells surrounded by the microstructure. Here, the cells are enclosed by the tiny structure, so it helps create a supportive environment where it mimics natural tissue, allowing for the cell to behave more like they would when inside the body. However, in all, photolithography is a really good tool to use in tissue engineering. It's allowed scientists to design surfaces that control how cells grow and interact. So it can lead to kind of better tissue development. So then we have soft lithography. The word lithography comes from litho, meaning stone. So it originally referred to a printing method using limestone plates to transfer patterns to paper. So this process is often associated with being solid and expensive because of the heavier material and more sophisticated equipment that it requires. So photolithography is actually a modern version of lithography. However, it still needs specialized clean rooms to control the conditions of temperature, humidity, keeping the dust out, and preventing any unwanted light that may affect the photoresist due to the light-sensitive material used in that process. So because of these requirements, photolithography can be very costly and can be hard to access. So we have two techniques in soft lithography. First, we have micro-contact printing. So this is a simple stamp method. So it's a stamp that's made from a pattern and is coated with a bioactive molecule. When the stamp is pressed onto the surface, it transfers the coating to that surface. So this method is generally very popular because it's easy and cost effective. So for tissue engineering, basically it's applied by creating a specific pattern for a molecule that helps cells stick onto the surface. So for example, you can control how cells organize themselves on different material by printing these patterns and applying that cell adhesive molecule onto the surface. Second, we have tissue micromolding. So this technique involves pouring liquid material like a biopolymer onto a flat surface, then using a soft mold, usually made from the photolithography process. That soft mold can fit onto the flat or surface due to its flexibility, and it allows it to create detailed shapes without damaging the material. So after the liquid solidifies, the soft mold is peeled off easily, reducing the risk of damaging the shape or the cells inside. So, for example, this technique can create hydrogel sheets with specific patterns. So, soft lithography is usually more accessible and has a versatile approach when creating tiny patterns. Um, and these patterns and processes can help support the growth of cells, which is very valuable in tissue engineering. So, microfluidics is a new technology that controls the flow of very tiny amounts of liquid, typically ranging from tens to hundreds of a microliter. So, this is much smaller than a regular drop of water. By carefully controlling the flow of these fluids inside of a microfluidic device, scientists can separate and detect substances with high precision, using only small amounts of sample material. Microfluidics is often combined with a tiny mechanical system called micrototal analysis system. This system aims to fully automate experiments onto a small microchip, combining many lab tasks into one device. So to make these microfluidic devices, they use a type of elastomer, for example, polydimethylsiloxane, which is actually very popular. It's popular due to its soft rubber-like material. That's also soft but flexible, so the flexibility makes it great for building tiny parts, um, like a microvalve or a stretchable membrane. This material is actually easy to make. So the devices are made through a simple process where the material is mixed and poured into a mold. It's then cured and then peeled off. So the simplicity makes it very popular for fabrication of it. This elastomer is actually clear, so you can see through it in the example to the right. So it makes it easy to observe experiments under a microscope. It also allows gases to pass through it, and is safe for living cells, which makes it perfect for biological experiments like growing and studying cells. This polydimethylsiloxane is actually a fairly easy material to bond. So um, it's like glass. It creates these microchannels and reserves that guide and store fluids inside of the microfluidic device. So microfluidics in tissue engineering is very useful because it allows very precise control over creating small tissues called microtissues by incorporating cells and hydrogels into a small fluid system. So microtissues can be designed to closely resemble the shape and function of tissues in the body. So microtissues have a small enough dimension to allow easy diffusion of oxygen and nutrients, which make them simple to grow in a normal condition without needing complex systems like bioreactors. Um, these microtissues can also be combined to form larger tissues depending on their shape. They'll be categorized into three different types. So pin-shaped, line-shaped, and planar shape microtissues. In summary, microfluidics is about controlling tiny fluid flow of high precision using that knowledge to make tiny tissues, which can resemble into a much larger structure, helping tissue engineers kind of mimic the body natural tissue growth.